Hi guys! In this video, we're going to talk about relative extrema and the second derivatives test. Let's start by recalling relative extrema of functions of one variable. So suppose we're given this graph of y equals f of x. Now, we consider the points near C3 and near C5. Note that for every x in some open interval around C3, f of x is less than or equal to f of C3. Similarly, for every x in some open interval around C5, f of x is less than or equal to f of C5. And so we say f has a relative maximum at x equal to C3 and at x equal to C5. On the other hand, uh, consider the point C4. Note that in some open interval around C4, we have the following property. F of x will be greater than or equal to f of C4 for every x in that open interval around C4. So we say f has a relative minimum at x equal to C4. Now, also remember that the tangent lines at the relative extrema are either horizontal or non-existent. Just like at C3, the tangent is non-existent. So f prime at C3 is undefined. On the other hand, at C4, we have a horizontal tangent line. So f prime of C4 is 0. At C5, we also have a horizontal tangent line. Therefore, f prime is 0. Now, we extend this concept to functions of two variables. So given f, a function of x and y, and let x naught, y naught be a point in the domain of f, we say that f of x naught, y naught is a relative maximum of f if f of x naught, y naught is greater than or equal to f of xy for all points xy in some open disk centered at x naught, y naught. We say that f of x naught, y naught is a relative minimum of f if f of x naught, y naught is less than or equal to f of xy for all points xy in some open disk centered at x naught, y naught. Now, if f has either a relative maximum or a relative minimum at x naught, y naught, then we say f has a relative extremum at x naught, y naught. Let's consider the function f of xy equals cosine x times sine y. Now, this is the graph of f. Intuitively, when we're thinking about relative extrema in terms of graphs, then relative maxima of functions of two variables are peaks, just as they are with single variable functions. Relative minima, on the other hand, will be the inverted peaks of the graph of the function. Now, to make things clear, these are the right or the correct terminologies. We say f has a relative extremum at x naught, y naught, or f of x naught, y naught is a relative extremum value of f. As an example, we consider f of xy equal to 4 minus x squared minus y squared, which is this paraboloid. It's easy to see that f has a relative maximum at the origin. Also, we note that the values of the first order partials at the origin are both 0. So that means we have a horizontal tangent plane at the point 0, 0, 4, or at the point where f has a relative maximum value. In general, we have the following theorem. If f has a relative extremum at x naught, y naught, and the first order partial derivatives of f exists at x naught y naught, and then the partial derivative of f with respect to x at x naught y naught must be 0, and the partial derivative of f with respect to y at x naught y naught must be 0. So to understand this result, it's uh, enough to consider slopes in the direction of x and in the direction of y. So let's say we have this graph which has a relative maximum at this point. Now, the curve in the x direction is this red curve, which clearly also has a relative maximum at the same point. So the slope of this of the tangent line at this relative maximum must be 0. So in other words, the partial of f with respect to x, since we're in the direction of the positive x-axis, must be 0. Similarly, the slope in the y direction must be 0, since this corresponds to the relative maximum of this surface. So this will also be a relative maximum of this green curve. So the tangent line at this point must also be horizontal. And so the partial derivative of f with respect to y must be 0. Note that the previous theorem provides a hint on how to find relative extrema of functions of two variables. Now, points which are possible or candidates for relative extrema are called critical points. And we define critical points formally as follows. Uh, So let's say f is a function of x and y. A point x naught y naught in the domain of f is called a critical point of f if any of the following holds. Number one, if both the partial of f with respect to x at x naught y naught and the partial of f with respect to y at x naught y naught is 0, or either fx at x naught y naught or fy at x naught y naught does not exist. Now we have the following remarks. If f has a relative extremum at the point x naught y naught, then necessarily x naught y naught is a critical point of f. But the converse of the first statement is not true. In other words, not all critical points give rise to a relative extremum. Let's take a look at the following example. So let's say we want to find the critical points of f of xy equals x squared minus y squared. And then we determine if these correspond to relative extrema of f. So since f is a polynomial in x and y, then we have no problem about the partial derivatives. They all exist at any point. Now we only need to solve the following equations simultaneously. So we equate fx to 0 and fy to 0. Clearly, the solution to this system is 0, 0. So we say the critical point, the only critical point of f is 0, 0. Now, to find out whether the sole critical point of f at the origin gives rise to a relative extremum, we consider the graph of f. We look at the traces. So in the xz plane, the trace is a parabola opening up with minimum at 0, 0. And on the yz plane, the trace is a parabola opening down with maximum at 0, 0. So there is some kind of a contradiction. Now, note that any open disk centered at the origin contains a portion of the parabola opening down and this parabola opening up. So by definition, f cannot have a relative maximum nor a relative minimum at 0, 0. In this case, we call 0, 0 a saddle point of f. In general, if P is a critical point of F, but F does not have a relative extremum at P, then most probably P is a saddle point of F. So now the question is, how do we know whether a critical point gives rise to a relative extremum without knowing the graph of F? For functions of one variable, we have the following steps in finding relative extrema of the function y equals f of x. So step one, we find the critical points of f. So that means we have to solve for those values of x for which f prime of x equals 0 or f prime of x does not exist. And then the second step is we use the second derivative test to determine the nature of the critical point. So we have to check whether f double prime is positive, negative, or 0 at the critical point. So note that if f double prime is positive, then we have a relative minimum at the critical point. If negative, then we have a relative maximum. And if 0, then we say uh, the critical point is an inflection point of f. Now, in the case of functions of two variables, we have similar steps in finding relative extrema of f of xy. So first, we have to find the critical points of f. That means solving for the equations fx equals 0 and fy equals 0 simultaneously, or fx does not exist, fy does not exist. Second step is to use the second derivatives test to determine whether f has a relative extremum at the critical point. Now, the second derivatives test for functions of two variables is a little bit complicated than its a single variable version. So here is the second derivatives test. Let f be a function of x and y with fx at the point x naught y naught equal to 0 and fy at the point x naught y naught equal to 0, where x naught y naught is a point in the domain of f. Now suppose the second order partial derivatives of f are all continuous on some disk centered at the point x naught y naught. Then we define the discriminant or the Hessian of f as follows. At the point x naught y naught, it's equal to fxx fy times fyy minus fxy squared evaluated at the point x naught y naught. So if this discriminant is positive and fxx at the point x naught y naught is also positive, then f has a relative minimum at x naught y naught. If d is positive and fxx is negative at the point x naught y naught, then f has a relative maximum at x naught y naught. If d is negative, then certainly f will have a saddle point at x naught y naught. And the remaining case where d equals 0, then we say that this test is inconclusive. Or in other words, f may or may not have a relative extremum or saddle point at x naught, y naught. Let's take a look at this example. So suppose f is 8 minus 3y squared minus 6xy minus 2x cubed. So we determine all relative extrema and saddle points of this function. So first step is solving the system fx equals 0, fy equals 0. So fx, or partial of f with respect to x, is negative 6y from this term, and then negative 6x squared from this term. And partial of f with respect to y is minus 6y from this, and we will get negative 6x from this term. So from equation 2, we have y equals negative x, and plugging into equation 1, we have 6x minus 6x squared equals 0. So we have to factor the left side to find to get all the possible solutions of this equation. So, and there are exactly two solutions, which are x equals 0 and x equals 1, and the corresponding y's are y equals 0 and y equals negative 1, which are obtained from this equation, y equals negative x. Therefore, we have two critical points. So the point 0, 0 and the point 1, negative 1. Next, we apply the second derivatives test to determine the nature of the obtained critical points. So we compute for the following second order partials of f. So fxx at y, we can verify that is negative 12x. fyy at any point xy will be negative 6, and fxy at any point xy is also negative 6. And therefore, we have this summary for this function. At the critical point 0, 0, fxx is 0, and at 1, negative 1, fxx is negative 12. Yes, times 1. fyy at the origin is negative 6, and at the point 1, negative 1 is also negative 6, since these second order partials are constant functions. So similarly, negative fxy is negative 6 at any point. So at 0, 0, it's negative 6. At 1, negative 1, it's negative 6. Now the Hessian, or the discriminant at 0, 0, so take note that this is the expression for the discriminant fxx times fyy minus fxy squared. So for fxx at 0, 0, we have 0. So this one becomes 0. fxy is negative 6. So the second term is 36. So we have negative 36 for D. And for the critical point at 1, negative 1, fxx is negative 12, fyy is negative 6. So fxx times fyy is 72 minus fxy squared. 72 minus 36 is 36. So for the point 0, 0, D is negative. So according to the second derivatives test, if D is negative, then the corresponding point is a saddle point. Now for the critical point 1, negative 1, D is positive, so we have to check the sign of fxx at 1, negative 1. Since it's negative, then by the second derivatives test, it must be a relative maximum. For our last example, we consider the function f of xy equals x cubed minus 3x squared plus y squared plus 2y minus 5. So let's start by finding the critical points of f. So we know that to find these critical points, we have to solve for the system of equation given by fx equals 0, fy equals 0. Now for this function, our fx is 3x squared minus 6xy equals 0. Let's call this equation 1. Fy is negative 3x squared plus 2y plus 2 equals 0. Let's call this equation 2. So from 1, we get this factorization 3x times x minus 2y equals 0. And that means either x is 0 or x is 2y if xy is a critical point. So in the case where x is 0, we can obtain the value of y by using equation 2. So from 2 we get 0 plus 2y plus 2 equals 0 or y equals negative 1. And so the critical point corresponding to this case is 0, negative 1. Next, let's consider the case x equals 2y. So when x is 2y, equation 2 becomes negative 3 times 4y squared plus 2y plus 2 equals 0. And factoring out negative 2, you get 6y minus y minus 1 equals 0. And then the quadratic factors in 2, 3y plus 1 times 2y minus 1 equals 0. Note that when y is negative 1/3, so the solution to this first equation, 3y plus 1 equals 0, is y equals negative 1/3. Its corresponding x-coordinate must be twice times this number, so negative 2/3. And when y is 1/2, the solution to the second linear equation, 2y minus 1 equals 0, we have x equals 2 times 1/2 or 1. And so the critical points arising from the second case are negative 2/3, negative 1/3, and 1, comma, 1/2. After obtaining the critical points of f, the next step is to determine the nature of these critical points using the second derivatives test. So we need to compute for the second order partials fxx. So fx is 3x squared minus 6xy. Therefore, fxx must be 6x minus 6y, or 6 times quantity x minus y. Fyy is 2, since this is your fy. Fxy is negative 6x. And we also have to compute the discriminant, which is fxx times fyy minus fxy squared. So for this function, the discriminant at any point xy is 2 times 6, 12 times quantity x minus y minus the square of fxy, so 36 x squared. And note that if we can show that d is negative at the critical point, then our conclusion is f has a saddle point at the critical point. Now, if d is positive and fxx is negative, then we say f has a relative maximum at the given point. Finally, if d is positive and fxx is also positive, then we say f has a relative minimum at the critical point. If d is 0, then we say the test is inconclusive. So we check the signs of fxx and the discriminant d at each of the critical points. So at 0, negative 1, clearly the sign of fxx is positive, while the sign of d is, since this is 0, 36 times 0 squared is 0, and this one is positive, then we have a positive discriminant at 0, negative 1. And we conclude that f has a relative minimum at 0, negative 1. At the next critical point, negative 2/3, comma, negative 1/3, note that fxx is 6 times negative 1/3, so negative. And at the discriminant will be 12 times negative 1/3, negative 4, minus a negative number is negative. So it's a saddle point. And finally, at 1, 1/2, this is 6 times 1/2, so 3. We have a positive fxx at 1, 1/2, while the discriminant d is 12 times 1/2, 6, minus 36, negative 30, so negative. And at the critical point 1, 1/2, we say f has a saddle point. And that's it. And there you have it for this topic. And as always, for your own sake, please do the following exercises. Okay, stay safe.